Okay, let's think about an example of an LTI system. I talked about an LTI system being a filter. Well, let's actually think about a filter. We're going to think about filtering some audio signal. So here is the audio signal. It's someone clapping and a cheer, but there's this awful high-pitched scream over the top of it. If we plot the sound amplitude like this, then we can see the claps occurring at regular intervals. The high-pitched scream is a solid block of blue. So this is the amplitude of the sound as a function of time. We can't see the individual oscillations because they're all too close together. Now, as we go through the next few slides, I'm going to paste up the Mathematica commands I used to generate these plots. It's a horrible sound again. I first import a sound file called noisyclaps.wave, which I'll make available, and I use the import command, and I'm going to give this the name claps. And this is a sound object in Mathematica. It's not a table of data, but it's actually a sound object, an audio object. I'm also going to define some plot options. These are just tells Mathematica how I want my plots to look with the aspect ratio and all this kind of stuff. And then to make this plot, I use a command called audioplot, which plots the time series of some audio object, audioplot of claps, including the plot options, and then labeling the axes. Okay, this time series is a little hard to interpret. Let's look at a spectrum. I can use a command called periodogram, which takes a spectrum, the energy spectrum, so it's this square of the Fourier transform, just looking at the positive frequencies, and plots it. So I'm taking the periodogram of claps with some labels on my axes, and the vertical axis here is energy. It's a decibel scale, and shows us how much energy we have in each of our frequencies. And we can see there's a massive amount of energy at this big spike here at 6,500 Hertz. So that's the frequency of this audio tone that we can hear. And we can see that we're down at around minus 30 dB here and up to plus 30 dB, so it's 60 dB different. So that is a factor of 1,000,000 times larger, 1,000,000 times more energy at this frequency compared to all the other frequencies. Now this spectrum, this plot of the spectral density, is taken over the entire time series like this. But we can see that the sound is changing as a function of time. We have the claps at these regular intervals. So a really useful technique is to divide the sound file up into shorter intervals and take a spectrum over lots of little short intervals and then paste the different spectra together so we can see how the spectrum of the sound changes as a function of time. So this is like an average over the entire file, but we can also do this where we divide it up so maybe 100 different spectra calculated per second, and we can see that when you have a clap, we have a lot of different frequencies, and every time there's a clap, we have this wide spread of frequencies from 0 up to the highest frequency in our file, which is 13,000 Hertz. And we have this big, long tone here at 6,500 Hertz, which is all the way through. Now, of course, a clap is some kind of approximation to a delta function, so you expect the delta function should have a wide range of frequencies, and indeed that is what we see, whereas this constant tone appears to be more or less a single frequency. We can also see the cheering here. That's what this little bit of the pattern here is. The color density, so the depth of the color here indicates higher power in each frequency. Okay, and the way you plot that is using a command called spectrogram. All right. Now, the thing we want to do next is try and filter out this big spike, this big, horrible, screechy spike at 6,500 Hertz. I mentioned previously the highest frequency here is 13,000 Hertz, which is telling us that's the Nyquist frequency, 13,000 Hertz, which tells us also that the sampling frequency of this file is 26,000 Hertz. So that's lower than a typical audio file, but it makes it a little easier to process. Let's look at the straight Fourier transform of our audio file now, because we're not going to filter the spectrum, we need to filter the actual Fourier data. Because if you remember our LTI system, we have the Fourier spectrum going in, and we're going to multiply it by some filter function or transfer function, g of omega, to get our output. So now we've got to design our filter. So to do that, we're going to look at the Fourier transform. So we've got a real part here and an imaginary part. And we see that the real part has a maximum amplitude of like plus or minus a half. The imaginary part, on the other hand, has these huge spikes at 6,500 Hertz and negative 6,500 Hertz. The plot of the frequencies here you can see is done in the default way for the computer to think about the Fourier transform. So it goes from 0 to plus the Nyquist frequency, then down to negative Nyquist frequency, and back up to 0. The first data point here is the 0 term, so that's where it tells you how much amplitude you have at 0 frequency. The last point here is a slight negative frequency just below 0. And the reason why I mention this becomes important in a bit. Okay, and we can also tell that our signal we're trying to filter is actually a sine wave, and we can tell because it's all in the imaginary component. If it were a cosine wave, it would all be in the real component, and if it's somewhere in between sine and cosine, we'd have a bit of amplitude in each. Okay, so the thing we're trying to filter out is a sine wave at 6,500 Hertz. And first of all, before I show you what we're going to do for filtering, I'll show you how I've plotted this data. So the clap data is the actual data I extract from the audio file. And the way I do that is I use a command called audio data on claps. So claps is the audio object. Audio data extracts it as just a table of data, so vectors of data. And this flatten command removes some of the curly brackets that Mathematica puts everywhere. The Fourier transform I take by using the command Fourier of clap data. And this is what I'm plotting here, the real part of FT clap data and the imaginary part of FT clap data. Most of the gumph that you see here is actually dedicated to getting axes labels on these plots from 0 up to plus 13 and minus 13 back to 0, because that's not something that Mathematica does lightly, so I've had to do that manually, so do it by hand if you like. So I've got some labels here that I use to label the x-axis. But anyway, here is the command list line plot for plotting the real part of FT clap data, and list line plot for plotting the imaginary part of FT clap data. Okay, onwards. What sort of filter do we want? Well, we want to have a filter that gets rid of these spikes. So basically we want to get rid of this part of the spectrum here. Now, this is the result after I've filtered it out. The kind of filter that I've used is basically the dumbest one you can think of, and that is I've got a vector of ones everywhere that I'm going to multiply my Fourier transform by, except for a narrow band of frequencies here and here where I've set that vector to 0. So when you multiply these two things together, you just let through all of the frequencies unaffected except for these ones here and here. And I've filtered out both the real and imaginary parts. To define that filter, that's a really simple idea, right? Just a big pile of ones. You multiply all of the frequency components by 1, except if it's here or here, and then it's 0. To actually define that filter is a little messy in Mathematica. So this is how I've done it. I've pasted together tables of 1s and 0s of the appropriate lengths. I know by measuring it that the number of data points I have in this data set is 97,066. And so the halfway point here up to plus 13,000 kilohertz from there to there will be 48,533. So that's where that number comes from. I just figured out by hand what this range of frequencies here is, which is from around index 24,000 to 24,500. Because it's numerical data, right? The numerical data is not labeled by frequency; it's just a string of numbers, and the number of numbers I have just depends on how long it is in the sampling rate. And so I've defined filters for the positive frequencies, that's from here to here, and a frequency for the negative part, which is from here to here. I've had to offset this by 1 here, so this is 24,002, this is 24,001. I've offset it by 1 index to account for the fact that my 0 frequency is here, whereas this one doesn't have a 0 in it. It goes up to a frequency just below 0 and slightly negative, which I mentioned before. And the final thing I have to do for this filter for the negative frequencies that run from here to here is reverse the order of the filter to mirror image it, because this is like a mirror image about this Nyquist frequency here. Okay, and then finally my filter is defined by sticking together the filter for the positive part and the reverse of the filter for the negative part. And now this is the step that I illustrated when I was talking about LTI systems. I take my filter, which is in this case G of omega, I multiply it by my input, which is FT clap data, and here I have the filtered output. And this is what I've plotted here, plotted the real part and the imaginary part. So to get my output, the time data back again, I'd have to take the inverse transform of this filtered data. And yeah, this is a note on this offset that I mentioned previously. Okay, so my filtered clap data would be the inverse Fourier transform of the filtered Fourier data. I've used a command called chop here to get rid of tiny imaginary components that get left over from the numerical Fourier transform. And so any imaginary number which is less than 10 to the minus 5 is just eliminated. And this gives me the data that I can then convert into an audio object that I can then listen to. All right, and I mentioned here to create that audio object, which I've called filtered clap sound, I've got to tell it what the sample rate is as well, because otherwise it doesn't know how to interpret the string of numbers. So in summary then, here's our input. And here is the filtered output, which has been inverse Fourier transformed. And so you can hear the sine wave there is basically gone. But I want you to listen to this again very, very closely. Turn up the volume and listen to the sound sort of immediately preceding and after the claps. If you listen really closely, you can hear something called a pre-echo. It's like a high-pitched sound that occurs just before the clap, or just before the clap and just after the clap. And this pre-echo is caused by the kind of filter that we used, which was like an upside-down top hat filter. And if you think about what a top hat is in the time domain, you can understand where this pre-echo is coming from. It's telling you this is a bad filter to use for audio. And we'll talk a bit more about filtering and the kinds of filters that work a bit later in another video. So in the context of our previous discussion about what Fourier transforms can do, this example of filtering an audio signal is this one here, where we start off with strange data. In this case, the strange data and the confusion is this bad noise, this spike at 6,500 Hertz. Now, if you want to get to better data, and we're trying to do it in the time domain, that would be laborious to impossible. If you're trying to remove this signal at 6,500 Hertz just by analyzing the time domain data, it's not even clear how you go about doing it, because you just look at the amplitude as a function of time. How do you decide which bits are due to the 6,500 Hertz signal, and how do you decide which bits are due to the clapping? So that's really hard. Instead, what we can do is go into the Fourier transform domain. So we go down here to the transform data. We do some simple, easy analysis where we just put a filter around our spikes, and that's easy analysis, and we can inverse transform to get our better data with our noise removed.